Hello, and welcome to this lecture in my series on the satisfiability problem for fragments of first-order logic. My name is Pratt-Hartmann, and today I'll be talking about the upper complexity bound for the two-variable fragment. I shall assume basic knowledge of first-order logic and complexity theory, and I'll be explaining the main ideas behind the proofs I'll be discussing today. However, I won't go through these proofs line by line. That's best done using a textbook, and if you want a reference, then I suggest my book on Fragments of First-Order Logic, section 3.2. The two-variable fragment, sometimes denoted FO2, is the fragment of first-order logic over a purely relational signature in which at most two logical variables, usually x and y, occur. And here's an example. So the first sentence says, every artist who admires some beekeeper despises some dentist. And this example says, every artist admires some beekeeper who hates every electrician. So you see these formulas are in FO2 because they feature only two variables, x and y. Notice that the variables x and y can be re-quantified here. So here I have re-quantified y. Y is quantified here, and it's also re-quantified here. It's no problem. Still only use two variables. X, again, I have quantified here and re-quantified even within its scope here. Again, that's still a valid formula of first-order logic. I should say a syntactically valid formula of first-order logic, and is perfectly correct, so that's in the two-variable fragment. Technically, we shall allow predicates of any arity, including arity greater than 2. However, in the context of FO2, these can all be replaced without essential loss of meaning by predicates of arity at most 2, so I'll assume all predicates are either one place, unary, or two place, binary. We don't need to worry about zero place predicates, that is propositional letters, because we can just guess their truth values. We can state in FO2 that a binary relation is reflexive or that it's symmetric. Here is the statement that R is reflexive, and here is a statement that R is symmetric. Clearly these only involve two variables. However, we can't obviously state that a binary relation is transitive. Here's the standard way of stating a relation is transitive. You take any x, y, and z. If rxy and ryz, then rxz. But that, of course, involves three variables, so that formula is not in the two-variable fragment. And we'll show at the end of this lecture that, in fact, it is not possible to express transitivity in the two-variable fragment. However clever you are, it just can't be done. So the next point to notice about the two-variable fragment is concerns constants and function symbols. The two-variable fragment has no function symbols, so those is simply not part of the fragment. All signatures will involve only relation symbols. Now, as far as individual constants are concerned, they can be allowed, but we shall, in this lecture, not allow them. And the reason is that individual constants can be essentially replaced by unary predicates, by one-place predicates. If you look at this sentence, you'll see how. So this sentence says there exists x such that there exists an x such that p of x. In other words, there are some p's, and if you take any two objects, x and y, and they satisfy p, then they're identical. In other words, there's at most one p. So that formula says there's exactly one object satisfying p. And so you can think of that can be used to simulate individual constants. So in the sequel, we shall have no individual constants, no function symbols, but we do have equality. Now, a formula of the two-variable fragment is said to be in Scott normal form if it has the shape shown here. Let's have a look at this. We have m plus 1 conjuncts here. The first conjunct is this thing here, it's universally quantified. It says if you take any two objects x and y, either they're equal or they satisfy alpha, where alpha is a quantifier-free, equality-free FO2 formula. In other words, a Boolean combination of atoms, not involving equality. So we think of this conjunct as being the universal constraint. Right? A set of these are our universal constraints. They say it says what happens to any pair of elements, whatever, in any model of our formula. Okay, so the remaining conjuncts all have the form of a universal quantifier followed by an existential quantifier, and it says for all x there exists y different from x, such that x and y are related by the formula BH, where h ranges from 1 to m. So as h ranges from 1 to m, we have a separate conjunct here. And the beta h is, again, a quantifier-free, equality-free FO2 formula. And these conjuncts we'll refer to as the witness requirements. So we have m witness requirements. Every object has to have a witness for each of the formulas BH, and that witness has to be distinct from itself. So we'll refer to y as the witness, or the ith. If we take the index h here, we'll refer to the variable, the object satisfying this existential quantifier as the hth witness for x, whatever x is. We have the following very important lemma. This is a lemma of a kind that is very widespread in the study of fragments of first-order logic. Let phi be a sentence of the two-variable fragment. It turns out that we can construct, in polynomial time, a formula psi of the FO2 of the two-variable fragment, such that psi is in normal form. It has the shape shown on the previous slide, and such that phi and psi are satisfiable over the same domains of size at least 2. Now, if we produce such, suppose we can prove this lemma, what that means is that when determining satisfiability in the two-variable fragment, we can confine attention to normal form formulas. Because if you give me any formula phi, I can use this lemma to produce a formula psi in normal form, which is satisfiable over exactly the same domains of size at least 2 as the original formula. If you look back to the formula, normal form formula, since m is positive, this formula can only be satisfied over domains of size 2 anyway. So testing the satisfiability of the formula phi, of the formula psi here, tests whether phi is satisfiable over domains of size at least 2. And of course we can easily test whether phi is satisfiable over domains of size 1, because that's just a problem in propositional logic. So this lemma is useful because it means that we can restrict attention if we want to determine the satisfiability of a formula phi to formulas which are in normal form. So let's see how we prove this lemma. So we'll start off with our sentence phi, an arbitrary formula in first-order logic, and we'll define phi 0 to be that sentence phi. By a sentence, as usual, I mean a formula with no free variables. Now, since this has got no free variables, well, I might as well, I can assume without loss of generality that this sentence begins for all x for all y, because if it doesn't, I can just prepend for all x for all y, and it will be true in exactly the same structures, so we can assume that without loss of generality. Now, suppose that phi I has been defined. I've defined phi 0. Suppose phi I has been defined. What I'll do is I'll pick an innermost quantified subformula of phi I. Okay, so that is a formula which has a subformula which starts with the quantifier, either for all x or for all y, or there exists x or there exists y, and then the scope, within the scope of that quantifier, there are no more quantifiers. So suppose that this subformula is theta, and let's just suppose that theta is existential. The argument where theta is universal is more or less the same. So theta has the form there exists v chi, where chi is quantifier free, and u and v are simply the formulas x and y in some order, right? So the quantified variable here is v. I'll denote that by v, but it's either x or y. And the other variable is potentially, I mean, in general, will be free in this formula. There are no more variables. There are only two variables, just x and y. So, of course, u might not actually occur free in theta. That doesn't really matter. We'll just we can write u here because potentially this formula theta has a free variable. Now, let P be a fresh unary predicate, a one-place predicate not occurring in any of the formulas we've examined so far. Okay, so what we're now going to do is define phi I plus 1 to be the result of replacing theta by the atomic formula P of u in phi I. So we have this formula phi I. We're going to choose an innermost quantified subformula, theta, with variable u, which may or may not occur free, and the quantified variable here is v. So we'll then replace theta by the atom P of u, where P is a new one-place predicate symbol. And that's my formula phi I plus 1. And then I'll define psi I plus 1 to be this formula which just asserts that P of u is true if and only if theta is true. There exists v chi is just the subformula theta. So I'll say P of u just has the same extension as theta. Pretty clearly, if I write the formula psi I plus 1, then phi I plus 1, which is just phi I with theta replaced by P of u, will entail phi I, because the formula psi I plus 1 says that P has the same extension as theta, and phi I plus 1 is just phi I with theta replaced by the atom P of u, so that must be that must be a validity. Conversely, if phi I has a model, then I can form a model of phi I plus 1 and psi I plus 1 simply by interpreting P, my new predicate, not occurring in phi I, but occurring in phi I plus 1 and psi I plus 1, by interpreting that new predicate to have as its extension simply the set of objects satisfying theta. So this conjunction here will be satisfiable over the same domains as phi I. Now, if you look here, I've done a little bit of judicious rewriting here. So instead of writing for all u P of u if and only if there exists v xi, I've rewritten this as for all u there exists v P of u implies xi, and for all u for all v xi implies P of u. And if you scratch your head a little bit, you will see that these two formulas are logically equivalent. So I'll take psi I plus 1 to be this formula in future. But notionally it's the same as the formula on the first line. Now, why is that? Why have I done that? Well, if you have a look at psi I plus 1, this formula psi I plus 1, it has the form for all u there exists v and then something quantifier free, and for all u for all v and then something quantifier free. So it's looking rather close to the normal form formula that we want to produce. It's not quite the same, but it's close. Okay, so what have we done? Given the formula phi I, we've produced a formula phi I plus 1 and a formula psi I plus 1, such that phi I and the conjunction of phi I plus 1 and psi I plus 1 are satisfiable over the same domains. Okay. If, by the way, theta is not existential, if it's universal, if it's for all v chi, then we proceed in exactly the same way, but making obvious adjustments. I won't go through this. It's more or less the same. So, carrying on. Proceeding in this way, we obtain, starting from phi 0, we get phi 1, phi 2, phi 3, phi 4, etc., producing along the way psi 1, psi 2, psi 3, psi 4. And you'll see that we'll, at some point after n iterations, we'll reach a formula phi n such that phi n and psi n minus 1, and etc., all the way down to psi 1, is satisfiable over the same domains as phi 0, that is to say phi, with phi n having the form for all x px. Why does phi n have the form for all x px? Well, because we prepended for all x for all y to the start of the formula phi, and that to get phi 0, and that will ensure that the event that right at on the outside we have a for all x, and then so eventually phi n will end up just with this form. We'll have a quantified subformula, and we'll just replace that with an atomic subformula where p is a new predicate. So that's what it will end up with. Now, when we remember the forms of all the psi's, universal conjoined with the universal existential formula, if we do some trivial logical rearrangement, this formula will have this form. It will be universal, and then alpha prime, where alpha prime is a quantifier-free formula, and a conjunction of universal existential formulas where beta h prime, each beta h prime is a quantifier-free formula. You may say, aha, well, maybe if we didn't do too much replacement, we'll m might be 0. In fact, m will have to be 1 because of all the quantifiers. Because we had so many quantifiers, we stuck to quantifiers on the front, so m is going to be positive in the end. Okay, so we're getting close. This isn't quite the normal form we want, but it's close. Okay, so the next stage. So let's have a look at this conjunction for all x for all y alpha prime. Over domains of size 2, this formula is logically equivalent to the following. For all x for all y, alpha prime x of x and alpha prime x of y, or x equals y. I mean, clearly alpha prime implies this formula. I mean, that's completely trivial. And over domains of size 2, it's pretty clear that the second formula implies the first formula. I mean, every pair of objects, if they're the same, well then if you take y to be any other object which you can over domains of size 2, then we have alpha prime x and x. So that's then any object is related to itself by alpha, and if x and y are different, of course, that immediately implies that x and y are related by alpha. So over domains of size 2, these two things are logically equivalent. And so what we can now do is let alpha be the result of replacing every occurrence of x equals x or y equals y in alpha prime xx and alpha prime xy, in other words, this formula here. We'll replace every occurrence of x equals x or of y equals y by top, because these formulas are trivial anyway, and they're clearly all true. And we'll replace every occurrence of x equals y or y equals x by bottom, because if x equals y or y equals x, then the second disjunct here is true anyway, so we're not going to affect the truth of the formula. So if we define alpha in that way, then we see that over domains of size 2, for all x, for all y, alpha prime is logically equivalent to for all x, for all y, alpha or x equals y. So we've got rid, so if alpha prime had some equalities, equality symbol thing, well, we've got rid of them and moved them out just to this disjunct here. And that's valid for domains of size at least 2. And similarly, we can replace the conjunct, these witness requirements for all x there exists y beta prime by for all x there exists y beta and x equals not equal to y, where beta is equality free. And over domains of a size at least 2, that replacement will be valid. And so when we perform that replacement, we will have a formula satisfiable if and only if phi is satisfiable, and that formula will be in Scott normal form. So it will be in the correct form and everything will be fine. That proves the theorem. It proves the lemma, I should say. So, in summary, given any formula of the two-variable fragment, with a little bit of rewriting, I can produce in polynomial time a formula in Scott normal form, in this form, which is satisfiable over the same domains of size at least 2 as the original formula. So if I want to test satisfiability, I can just assume without loss of generality that formula is in this form. Now we'll need a bit of apparatus to give a decidability proof for the two-variable fragment, but this apparatus is relatively intuitive and widely used in studies of decidable fragments, so it's worth getting clear about how it works. Let sigma be a purely relational signature, so no constants or function symbols, in which all predicates have arity at least 1, so no proposition letters. A literal over that signature is an atomic formula or the negation of an atomic formula, so something like this: px1, not px1, not qx1x2, qx1x2, qx2x2. Okay, so that's a literal. A k-type is a maximal consistent set of equality-free literals over sigma involving no variables other than x1 up to xk. Think of a k-type as a complete specification of the relations determined by some structure on a particular selection of k individuals. Usually we will assume these individuals are distinct. I'll come on to that later. But a k-type, formally, is simply a maximal complete set of literals, equality-free literals, over some fixed signature sigma, involving variables, no variables other than x1 to xk. Let's have a look at some examples. So what about a one-type? If we have, if we sort of fix a signature as sigma to consist of the predicates p and q, where p has arity 1, it's unary, and q has arity 2, it's binary, then this is a one-type. We'll say that px1 is true and qx1x1 is true. We can't add any more literals over the signature in just involving the variable x1, so that is a one-type, and remain consistent, so that's a one-type. Here's a two-type. We'll say that px1, px2, qx1x1, not qx1x2, qx2x1, not qx2x2. Okay, so we can't add any more literals over this signature involving the variables just x1 and x2 without getting an inconsistency. So this is a maximal consistent set of literals over that signature involving variables x1 and x2 only. And we can picture this thing as follows. Here's x1, here's x2, and so x1 has these properties, px1, qx1, x1, x2 has these properties, as shown here, and the pair x1, x2 has the property not qx1, x2, and the pair x1, x2 has the property q. The pair x2, x1 has the property q, x2, x1. So that's a two-type. If sigma features s predicates, then the number of one-types is easily seen to be at most 2 to the s, and the number of two-types is easily seen to be at most 2 to the 4s. That's a simple calculation. I'll leave you to check that. If A is any structure interpreting this signature sigma, and A bar is a tuple of elements. Okay, we'll generally want to assume they're distinct, but it doesn't really matter for present purposes. There exists a unique k-type satisfied by that tuple. I mean, you just look at the predicates satisfied by the tuple in question, and that determines a k-type in the obvious way. So we'll call that k-type the k-type of the tuple A1 to AK in the structure A, and we'll denote it type superscript structure square brackets tuple. In effect, the k-type of the tuple, the type of the k-tuple A in the structure German A is a picture of the structure restricted to the subset A1 to AK of elements. Think of things that way. It's probably easier. Okay, since the signature is finite, so are k-types. These are finite sets of literals. So we can silently identify k-types with their conjunctions. For example, the k-type consisting of the one type consisting of the literals p1 and not q x1 x1 can be identified with this conjunction here, and the two type consisting of this collection of literals here can be identified with its conjunction in the usual way. So it's just that if k-types are, since k-types are finite, and they will be if the signature is finite, then we can just think of them as single formulas. Okay, so when we're dealing with one types, we will, instead of talking about the variable x1, we'll use x, and when we're talking about two types, instead of using the variables x1 and x2, we'll talk about x and y. This is just a little bit more user-friendly, of course. It's purely cosmetic change. Recall that the two-variable fragment can express the condition that some formula psi is uniquely instantiated. So this formula will do it. It will say there's some object satisfying psi, and any two objects satisfying psi are identical, so there's exactly one. And an element, now you think about the case where psi is a one type, which we can again think of as a formula. An element of a structure German A, whose one type is uniquely instantiated, is called the king, and the one type in question is called royal. Note that whether a one type is royal or not depends on the structure. So you can't talk about a one type as being royal absolutely. It's always royal with respect to some fixed structure, right? So if I've got a structure in mind, some one types will be royal, others won't be. Okay, so if A interprets a purely relational structure with S predicates, then the set of kings in that structure satisfies the condition that its cardinality is at most 2 to the S, because that's the number of one types. I mean, there can only be one king of any given one type by definition. That's what a king is. Okay, so we know that the number of kings in any structure is bounded exponentially as the size of the signature. Okay, next idea. Suppose we have a formula in Scott normal form which is satisfied in some structure. I'll use the following terminology. It helps to talk about things a little bit more succinctly. If we have an element A in the domain of that structure, there must exist, if you look at these contracts here, there must exist elements B1 to Bm such that for all H, the pair A, B, H satisfies B to H. And moreover, the elements B1 to Bm have to be distinct from A, of course, simply because the structure A is assumed to make these formulas true. And of course, there may be more than one suitable candidate for these elements B1 to Bm, but we can just choose one at random. We know that we must be able to do that if the formula is true. So, having chosen them, we'll call BH the eighth witness with respect to A. Given any element A, we can choose a collection of witnesses. We know they must exist. We'll just make that choice and forget about it after that. Okay. Now, again, continuing under our supposition that phi is a formula in Scott normal form, satisfied in some structure A. Let K be the set of kings. Each of these kings will have witnesses, M witnesses. By the way, these witnesses need not be distinct, but there's going to be at most M of them anyway. We'll say that the court is the subset of the domain consisting of the kings and all their witnesses. There are at most exponentially many kings, and each king has at most M, in other words, linearly many witnesses. Okay, very important idea. So in any model of normal form formula, actually, I suppose in any model of any formula, but the notion clearly applies to normal form formulas. In any model of a normal form formula, there's a set of kings, at most exponentially many, and each of these kings has M witnesses, defined in this way. Okay, so we're now going to prove the following lemma. Let phi be a satisfiable formula of the two-variable fragment in Scott normal form over a signature sigma of unary and binary predicates. Then phi has a model of size bounded by this function here. The exact details of the bound aren't really important. The important part is that the bound is exponential in the size of the original formula. Okay, let's see why this lemma is true, and then we'll use the lemma to prove decidability of the two-variable fragment for satisfiability. Okay, so let's have a look. So here's the lemma. Remember, we've given a formula of two-variable fragment in Scott normal form. It's got its universal constraints. It's got its witness requirements. Signature of size, let's say S. We've got to show that there's if there's a model at all, if it's satisfiable, then there's a model of exponential size. Okay, let's go. So we're assuming that here's our formula, it's got normal form. We're assuming that it's satisfiable, so we can write our model, we'll call it German A as usual. And this model has a bunch of kings, at most exponentially many of them. These kings have witnesses. Each king has at most M witnesses, and they form the court. Of course, a witness of a king may be a king, but that's no problem. It's still got a bound on the size. This is our court. The model A may contain other elements, perhaps infinitely many elements. We don't know anything about it. But the bit of A that we care about is the kings and its court. What we're going to do is get rid of all these other elements. You could call them the common elements, and we're going to replace them with something else. Of course, if we simply got rid of the elements of A, then the kings would, and then just look at the substructure consisting of the court, then the kings would all have witnesses, they'd be fine, but the poor old courtiers here stuck out in the court may be lacking witnesses, because maybe some of their witnesses were in the common elements and we've got rid of them. So we need to find replacements. So let's see how we find replacements. Notice that if we have any element of the original structure, let's think about the original structure A. If we have any element of the original structure A, it will have a one type, let's say pi1, doesn't really matter what the one type is, and it will have M witnesses, and these witnesses will have one types. So the first witness may have one type pi1, and then the second may also have witness of one type pi1. Maybe the last witness has, last but one witness has one type pi n, where n is some nice big number, and the last witness, the nth witness, may have one type pi2. They're just one types. So every element of the original model A will have a one type, and it will have witnesses having various one types. And the pair consisting of the original element and each of its witnesses will have a two type. Okay. So here's what we'll do to find witnesses for the courtiers. So we've got the king, here's the court, so this is the original model restricted to the court. We've got rid of all the commoners, and we need to find witnesses for the courtiers. And I'll manufacture witnesses for the courtiers in this area here. So you'll see I've drawn 3 blocks of elements. Each block has rows labelled by the one types that occur more than once in the original structure A. These are the non-royal one types. I'll just write them as pi1 to pi big N. And the columns are simply labelled 1 to m, corresponding to the witness requirements, h1 to hm. H equals 1 to h equals m, I should say. And so that's what each of these blocks looks like. It's just a block of elements, and I'll choose 3 such blocks, and I'll explain in a moment why we want 3 blocks of these elements. But these will just be elements, and what I'm going to do is take the original structure restricted to the court, that's of exponential size, and I'll add as new elements these blocks. And since there are exponentially many one types, only linearly many indices for witness requirements, this whole, and only 3 blocks, then this whole structure, the whole thing, is bounded exponentially as a function of the original formula phi. So this will be a small model of phi, and I'm going to turn this collection of elements into a model. It's defined on C. I haven't defined the model on these new elements. Okay, so the first thing I have to do is to set up the one types for all these new elements. Well, that's easy. If an element is in a row labelled by the non-royal one type pi, I will just give that element the one type pi. So all the elements in this row will have one type pi1, all the elements in this row will have one type pi2, and so on. So I've now defined the one type for all of the elements. I've now got to define the two types for the elements. So how do we do that? Well, let's have a look. So we know that the two types are defined within the court here, because we've just taken those over from the original model A. So suppose that we have an element of the court. It will require various witnesses. And those witnesses will have all sorts of different, will require all sorts of different one types, right? We'll have all sorts of different one types in the original model. So we take a court here, look at its witnesses in the original model. They may have disappeared because they may be common elements. We'll just look at their one types. If its first witness has one type, say pi3, I will choose the element in the row labelled pi3 in this first block. And because I'm after the first witness, I choose the first column, and I'll say, right, that element has one type pi3. I can set the two type between this element and that element to be something that satisfies beta 1. What I'll do is I'll take it to be the two type between this element and its first witness in the original model. Clearly, if I set this two type to be the same two type, everything will be consistent. So I can find the first witness. And of course I can find all the other witnesses as well. I can find the second witness in the second column, the third witness in the third column. I've got plenty of elements to choose from. If the witnesses are required to be non-royal, so in other words, they're common elements, so they'll certainly have non-royal one types, I can certainly find a row corresponding to the appropriate one type and give every element in the court a witness if it lacks one. Of course, if an element of the court has a witness already that's already in the court, then that witness will still exist because we've just taken over the substructure restricted to the court into the structure we're now defining. So I can make sure that every quartier has a witness, and I only need elements of the first block to do this. And I can get all of the witnesses for all of the quartiers, and there'll be clearly no clashes. What about finding witnesses for elements of the first block? How do I do that? Well, this element will have one type pi1. I know that there will be a common element, an element occurring whose one type occurs more than once in the original model. And I can just choose such an element and see what witnesses it has. Suppose that its first witness is a king. Well, if its first witness is a king, then I can easily just choose the appropriate king to be the witness and just set the two type up accordingly. There'll never be a clash because kings already had witnesses in the court, and the only witnesses only elements I chose to be witnesses for the elements of the court were witnesses for courtiers, not for kings. So if I require a king as a witness, I can just choose the appropriate king as a witness, no problem. It may be that if I've chosen an element of common one type pi1 here, it may require witnesses of common one type. Well, here, if I want to do that, all I have to do is choose elements in the second block in the obvious way. So suppose I want, let's say, suppose I want the first witness to be a common element having one type pi2. Well, I'll look at the second block because I'm choosing elements in the second block. First column because I'm interested in the first witness, and I'll choose the type pi2. If I want the second witness to have type pi(n), this last column, then I can choose the nth row of the second column, nth row, and set the two type between this element and that element in such a way that this element now has its second witness. And I can just go on and set all the types accordingly. Remember that if I require a king as a witness, that's no problem. I can just set the two type between this element and the king. So in this way, I can ensure that every element of this first block, because I can treat all the elements of the first block in the same way, has a witness in the second block. So, and what do I do with the elements of the second block? Well, I'll choose elements of the third block to be their witnesses, or kings as appropriate. And what do I do with elements of the third block? Well, I'll choose elements of the first block to be their witnesses, again using the same pattern. I'll never get confused, I'll never overwrite anything because these have witnesses in there, these have witnesses in there, those have witnesses in there, and then I'm done. And so there's no overwriting going on. When I've finished this whole process, every element will have a one type, and every element will have m witnesses chosen for it, satisfying the witness requirements. Furthermore, all of the two types I'll have set, when I set these, chosen all the witnesses and set these two types up, will satisfy the universal requirements because there'll simply be two types chosen from the original structure, and those satisfy by hypothesis the universal requirements. So I'll have fixed witnesses for all of the elements in this structure, and so all the witness requirements will be satisfied, and none of the universal constraints will be violated. So, and the final point is that if you look at the size of this model, it's exponential. So it looks like I've got an exponential size model for my original formula phi. There's one slight snag. In order to have an actual model, I have to define all the two types, all the one types and all the two types. There are no predicates of arity greater than 2, assuming that everything has arity 1 or 2 in the two-variable fragment. So I only need to define one types and two types. But it may well be that there are pairs of elements whose two type I haven't fixed, and I need to make sure that I can do that consistently. Well, let's think. Suppose we take such a pair of elements, and I've chosen this element here and that element there. And suppose that, having fixed all the witnesses, the 2 type between these 2 elements has not been defined. Can I define it consistently with alpha? Well, we know that this 2 type, let's look at the more interesting case where these 2 elements have the same 2 type. That 2 type might be same 1 type, I beg your pardon. So these 2 elements whose 2 type has not been defined have the same 1 type. Let's say that's pi3, just for definiteness. So I know that there must be elements in the original structure having this 1 type. In fact, I know that there must be more than 1 such element. Why? Because these 1 types are common, they are non-royal. So by definition, they are realized in the original structure more than once. So, given that this 1 type is realized more than once, I can take 2 distinct elements in the original structure, having the 1 type pi3, look at their 2 type in the original structure, A, and simply set this 2 type to be that 2 type there. And of course, the universal, when I do that, the universal constraints won't be violated because they weren't violated in the original structure, and I've just copied the 2 type over. If the 2 types in question, if you have a pair of elements with different 2 types, in other words, in different rows, then if I choose elements in the original structure having those 1 types, then clearly must be different. So again, I can just take the 2 type of that pair of elements and then copy it over. You see that we have to be careful that the elements we're choosing to copy the 2 types from are different in the original structure, because we have 2 distinct elements here, and if we're choosing elements in the original structure with this common 1 type, then we have to, in order to define a 2 type coherently, that that we must ensure that the elements are distinct, because if they were the same and that 2 type is not symmetrical, then we would get if the 2 types required by alpha are not symmetrical, then we would get a clash. We wouldn't be able to find an element of the 1 type, an element of the appropriate. We wouldn't be able to find 2 distinct elements of the appropriate 1 type in the original structure. Okay, so that once we've done that, we've completely defined the structure. Everything is okay. We've got we haven't violated the universal constraints. We've satisfied all the witness requirements. The whole thing's of exponential size. So on the assumption that phi has a model at all, we can show that phi has an exponential size model. Of course, it easily follows from this that the satisfiability problem for the 2-variable fragment is in non-deterministic exponential time, and we can show this by simply guessing and checking a model of subject to the given exponential size bound, and that's clearly doable in non-deterministic exponential time. I won't go into the details. You have to be a little bit careful, but it's routine. As a corollary of this proof, we see that the fragment FO2 has the finite model property. That is, if a formula is satisfiable, then it's finitely satisfiable. This must be true because if a formula is satisfiable, we can build a model of exponential size, and that is clearly finite. So the formula, the fragment FO2 has the finite model property. The satisfiability problem and the finite satisfiability problem are the same problem. It's possible to obtain a matching lower bound. We have the following lever. The satisfiability problem for FO2 is NExpTime hard. In other words, if we put those 2 together, we get as a theorem, the satisfiability problem for the 2-variable fragment is NExpTime complete. I won't go through the proof of the lower bound. That can be done perhaps in another lecture. I'll just mention that the easiest proof is by reduction from the exponential size tiling problem. For those who know it, it's a relatively straightforward, rather technical exercise, and I won't be talking about that today. So I'll finish with, if you like, dessert, which is a proof that transitivity cannot be expressed in the two-variable fragment. So I mentioned earlier that there doesn't appear to be an FO2 formula saying that R is transitive, and the most obvious way of saying that R is transitive requires three variables. You might think, well, maybe there's some clever reuse of variables, some complicated formula that is logically equivalent to the transitivity requirement, but still only uses two variables. But the finite model property for the two-variable fragment shows that that cannot be the case, because if R is a transitive relation, then this formula is satisfiable but only in infinite structures. Let's have a look at this formula. It says that for all x, there exists a y such that Rxy. So everything is related by R to something. R is serial. And this formula says that nothing is related by R to itself. So it's pretty clear that so if you take any object in any structure, it has to have, in any model, then it has to have something, has to have an R witness, that has to have an R witness, that has to have an R witness, and so on and so forth. And it's pretty clear that as you take successive R witnesses, you can't reuse any of them elements you've already generated in that sequence, because if you did, you'd have a loop of R's, and since R is transitive, you would violate this requirement. So this is a two-variable formula, apart, of course, from the requirement that R is transitive. So if transitivity were expressible in FO2, then the FO2 would lack the finite model property, and it has it. So transitivity is not expressible in FO2. So let me summarize. It's the end of the lecture. We've examined the two-variable fragment of first-order logic, usually denoted FO2. So in this fragment, we've got just two logical variables, x and y. We allow equality. We can have individual constants and predicates of arity higher than 2, but they don't add meaningful expressive power, so we usually ignore them. We do not have function symbols. We proved the normal form theorem for FO2, so every formula of FO2 is equisatisfiable with a formula in so-called Scott normal form over domains of size at least 2. And we used that to prove an exponential size model property for FO2. And it followed from that FO2 is in NExpTime and that the fragment has the satisfiability problem for FO2 is in NExpTime, and that FO2 has the finite model property. We stated a matching lower bound, but we didn't prove it. And finally, we used the finite model property for FO2 to show that transitivity is not expressible in FO2.